All right, we have 9-1, day 1. We're introducing the idea of a significance test. Just a little overview of Chapter 9. In the first section, we'll kind of get this idea out there, what a significance test is, and then, especially how it's different from confidence intervals. And then in 9.2, we'll dive into all the specifics of how they work with proportions, and then in 3, we'll look at means. So this slide is really just giving us some context to talk about, okay? Here's the idea. We're still working with a sample. We're still trying to make a conclusion about a population, but we're testing a specific value that we think the parameter might be. Okay, something about the problem gives us a reason to suspect a certain value, like an individual that claims they make 80% of their free throws. So we're like, okay, this would be a proportion, that P is 0.8. Let's test the idea that P is 0.8. Okay, so we do a random sample of 50, and the individual makes 64%, which is right down here. Okay? Right down there. Which is less, right? It makes us think, maybe they're not as good a free throw shooter as they think. Maybe they're less than 0.8. Okay? Because this sampling distribution, which notice it looks normal, right? In fact, 50 times P would be 40, and 1 minus P would be 10, right? Because we'll still have the normal condition. I'm just throwing it out there in this one that it's met, which is why you're seeing the sampling distribution, which isn't the actual one. It has 400 random samples, but it looks pretty normal. Okay, it does. It looks like there's only 3 outcomes of the 400 that involve making 64% or less. So this seems to be pretty unlikely that would just happen. Due to bad luck, okay? Because really there's 2 ways to explain this scenario. Number 1, the player's claim is correct and they had really, really bad luck and they just had a horrible shooting day. Or option number 2, the player's claim of being an 80% free throw shooter actually isn't true. That's the other possibility, okay? Notice that basic idea down there is a big one, okay? If we're trying to reject the claim, and that's kind of the approach that we take, is to see, could we find evidence to reject their claim? An outcome that would rarely happen if the claim were true is good evidence that the claim isn't true, okay? And that's what we're seeing on this example. Their claim is that they're an 80% free throw shooter, but we see if that's true, it looks like from the sampling distribution, the probability that you would shoot 50 and only make 64% looks to be low, which makes us doubt their claim. So this summary right here is basically what we call our state step. This looks a little bit different because we're now doing a test, not constructing an interval. You'll have 2 of them, HO and HA. HO is always set up as an equal sign, okay? We have the example for the basketball data down below, right? HO is down here. That is the claim that the individual made, that they make 80% of their free throws. So let's say that's true. We suspect it's less. So we said that HA is states that P is less than 0.8. This last part is the same as a confidence interval that, we have to define the parameter. Okay, just like we did with, if we're constructing a confidence interval for P in our state step, then we had to go say what P was. Okay, here's the same. Like once we're introducing a parameter, we got to define what it is. Okay, but that's really those three parts is what your state step would have. A couple other things about hypotheses. HO is never really going to vary. It's always just going to say the parameter equals some value. HA can, it could be less than. That's the one we're looking at as a less than. Could be a greater than. If we're really not sure which side to be on for HA, then we could do a two-sided test and just say not equals the value. And the one we're looking at, it's a less than because we suspect this free throw shooter, if you read through the context, we think that they're claiming to be a little better than they actually are. Okay? That's what we think P is possibly less than 0.8. All right, so I got this golfer who wants more consistency out of his 7-iron. Okay, so this is kind of an interesting one. We're essentially writing the state step. I'll put a note in here that if we were doing a significance test on this, this would be your state step. This one involves a standard deviation. We typically wouldn't do that. Sometimes we just look at kind of parts of doing a test on a different measurement, but I think you guys know by now, for a full 4-step, we would do a proportion or we would do a mean. And those are the only two that we would do. Okay? There's HO. Okay? We'll say that sigma is 15. Okay? That was the standard deviation of his old 7-iron, so we're going to assume that the new one isn't any better. We're going to have to be convinced to say that it's better. That's what we're hoping. So this would be a one-sided. It would again be a less than. Now the third thing I have to have is I need to define sigma. It's the true standard deviation. One thing I'm going to add to this in terms of context, my units are yards, and in HO and HI I didn't say that, and realistically I should. It's not a deal breaker if I didn't, because I can go right here and just add it. Standard deviation in yards. Of balls hit with the new 7-iron. So that would be your state step. We have HO, and you're going to hear me come back to this point a ton. It's really, really important to remember. We'll get to it on the next slide because it comes up again and again. But it's actually honestly overlooked a lot in 4 steps. Throughout the test, HO is assumed to be true. Okay? It's a big thing to know about HO. So as we're doing this test, and he's taking a random sample of shots with his new 7-iron, at the beginning of the test, we are assuming it's no better. Right? He wants more consistency on the shots. So each one goes closer and closer to the same distance of about 175. We're assuming the new one is no better. We need evidence to convince us that it is. That gets into HA. Now, we talked about how if the probability of our sample measurement occurring is really low, that's good evidence against HO. We call that number a p-value. So this definition is really important. And again, I'll highlight this first part because it so often gets overlooked. It is a probability calculated under the assumption HO is true. Okay, that the statistic that we got would be as extreme or more extreme than the one we obtained. Okay, when we say extreme, it's how far it is away from the center. Okay. Interpreting p-values can be a little bit tricky. We'll get to that a little later on. The bigger part right now is down below. You should get comfortable with this idea. Small p-values are evidence against HO. Large p-values are not. Okay? Small p-values are evidence against HO. Large ones aren't. Okay? We'll get into a little more as to what's big and what's small. If we do have a small p-value, okay, this is kind of getting into our conclusion. We come to two conclusions. Okay, we reject HO, or we'll fail to reject it. Those are the only two possibilities as far as what we could conclude. Now look down to the bottom here. If the p-value is small, we'd reject HO. That means we are going to conclude, and we'll kind of state one sentence as far as what that means. We'll conclude HA, right? Because we are convinced that we think HA is true. If the p-value is large, we'll fail to reject, and then we'll state that basically we can't conclude that HA is true. Okay? If we're going to say that HA is true in our conclusion, we had to have said that we are rejecting HO. All right, so we have a p-value. Mike goes and hits some shots with the new 7-iron. They go pretty well. Standard deviation was 10.9. Okay, 10.9. We were assuming that it was going to be 15, and it was lower. And it turns out it was a lot lower. Okay, the p-value kind of tells us how extreme it was. If the new club isn't any more accurate, and he just got really, really lucky with this set of 50 shots, there's a 0.002 chance that he would get a sample standard deviation of 10.9 or lower, just because of random chance. Okay? Doesn't seem like it was due to chance. It's just way too low. The better conclusion is that the new club is more accurate. Okay? So do we have convincing evidence I would say, yeah, 0.002 That's a really small p-value, so we will reject HO, right? The hypotheses are still up at the top. We're going to reject HO. We're convinced that sigma is less than 15 yards, for the new 7-iron. So it's not enough just to see that S was below 15. It has to be significant, but the nice tool that we have is the p-value tells us that. Like, how far below 15 were we? Right? If the p-value is really small, then it's more likely we'll be convinced that we can reject HO. All right, so now we have to get really specific, right? We can't just be as broad as to say, if p is small, reject HO. If the p-value is large, then don't. We have to have a cutoff as to where we'll reject and where we will fail to reject. Okay, that cutoff is called alpha. Okay, that's what this next blue box is saying. Here's what you'll find. Technically, you can set alpha, well, not to anything. It's the cutoff for a p-value, so it's got to be between 0 and 1. Those are the three you're typically going to see. 0.1, 0.05, and 0.01. Go one of two ways with alpha. If the problem states what it is, obviously use that alpha value. If it's not stated, then just use 0.05. Okay? Now here's a new context. Another project. Student decided to investigate if students at their school prefer name brand potato chips or not. I'm just going to do this one at alpha 0.01. So they did the taste test, right? And P is the true proportion of students that prefer name brand. So HO said that it is 0.5. HA says that it's greater than 0.5. So the students doing this project were suspecting that they kind of think students are going to prefer the name brand. That's what they're leaning towards, which is why HA is greater than. So they crunch their data and they get a p-value of 0.0055. Okay? Which again, I don't want you to be too concerned yet with interpreting that value. That will be something that we'll have to do here pretty soon. Okay? But this is basically your conclude step, by the way, now that we have an alpha value, which is right. We're saying we're testing at 0.01. Here's what our conclude would look like. Since 0.0055 is less than 0.01, okay? If you need to, refer back to the other notes about what we do. Reject or fail to reject. This is a case where alpha, the p-value is less than alpha. We reject HO. Now our notes have said we need to state one sentence about HA that we're convinced that it's true. Okay. Well, HA says that P is greater than 0.5, so that would mean basically that we have convincing evidence that the students at this school prefer name brand potato chips. So that's exactly what I'm going to say. Notice I'm doing it in context. Talking about students, talking about this particular high school. Prefer name brand potato chips. Right? HA said that they prefer the name brand. I'm just saying that I'm convinced that that's true. Think of those two going together. We have two hypotheses. Okay? And look at what we did right after we compared the p-value to alpha. We rejected HO. We said, you know, we do not think that that one's true. Okay? That leaves us to conclude HA. This is just summarizing the conclude step. You just saw it. I'm just breaking down to the three parts. Okay? So really the two parts that you'll see are really, really different in the fourth step are, well, not really different, but they do look different to some degree, the state and the conclude. Okay? So number one, we have the explicit comparison of the p-value to alpha. We make a decision about HO, reject or fail to reject. Give an explanation about what it means in context. Right? That explanation will always be in terms of HA.